things seem to be completely clear. The direct model with first-order coupling is equivalent. When I say equivalent, it's like mathematically equivalent to the rotated region coupling. So if there's going to be any quantum print, we're going to have to, and the next slide, I would say, descending into madness, because that's the only possible thing that could pop up from here. So I'm thinking about the Foldy-Waldhusen constraint. So I want to rethink the problem. I start with this. Foldy-Waldhusen is in this. There's the coupling. The coupling's gone. So as long as I can do Foldy-Waldhusen, I'm going to eliminate the first order coupling. I'm going to have no joy. So the question is, there we go. But this is madness. It seems that the only way that there's going to be a resolution to this is if Foldy-Waldhusen breaks. And I use breaks with a quote. Now, Foldy-Waldhusen appears in, this rotation appears like everywhere in physics, and not everywhere in physics. This Foldy-Waldhusen is the foundation for our understanding of non-relativistic physics. We start with Dirac type formulation, relativistic formulation. Foldy-Waldhusen takes us to the non-relativistic, clean separate law. It does take us on non-relativistic, but the more important thing it does is it eliminates the first order coupling between the internal nuclear degrees of freedom and the center of mass. Also, it's just a simple basis change. So, if you like basis change can't break, it doesn't make any sense. But the question is there a place where Foldy-Waldhusen doesn't work? Turns out, here's some fine print. Let me go back to the spin boson model. The spin boson model is actually very similar. And in the spin boson model, if there's no loss, I can use Foldy-Waldhusen, and I can describe multi-quantum transitions, and I can eliminate the first order coupling. But on the other hand, if I have loss to the spin boson model, then if I do Foldy-Waldhusen, I can get a transform version of the problem. But the transform version of the problem isn't like interesting or relevant because the loss gets rotated too, and it turns into a big ugly mess. So I gotta be more careful. I mean, like, Foldy-Waldhusen broke with quotes when dealing with the lossy spin boson model. So let me go back and let me think about it. Spin boson model and part of the Dirac proton vibrational system. So mass, energy, positive mass, negative energy, upper state, lower state. These terms, they're like the same. Oscillator, any oscillators. Oscillators are oscillators. Transitions. So takes me from up to down and exchanges a quantum. Takes me from up and down, exchanges a quantum. These problems are really closely related. And in the spin boson model, I have an example where Foldy-Waldhusen is breaking. So I'm looking at the possibility of there actually being some fine print here. And this is interesting. Foldy-Waldhusen applied to spin boson. Well, we published several papers in JPhysB 2008. We can use it to describe coherent energy exchange in multi-quantum regimes, so it's incredibly closely related to this problem. When augmented with loss, the coherent energy exchange that we talked about is enhanced by orders of magnitude, and it acts as if Foldy-Waldhusen breaks in this system. Breaks with quotes. And Foldy-Waldhusen can't break, but it just gives you a system that's not helpful. Okay, why might a rotation break with quotes? Suppose I start out with a problem that's loss-free that I can rotate. It's got first-order coupling. Now I have loss. Well, the rotated version of the problem gives me something where the first order coupling is eliminated, but that same rotation has to rotate the loss. And the argument is if this becomes a mess, there's conditions under which there's parts of the problem where the loss very, very, very strong. And when you rotate it, it's quite possible that this rotation is going to lead to a mess that's going to make this problem intractable. And in this case, the rotation is unhelpful, and it's better just to work with the lossy problem directly by brute force. And in that sense, the argument is that the Foley-Wolthusen transformation breaks with quotes. Not that it breaks, never breaks, it becomes unhelpful. Takeaway message. We've succeeded in finding some fine print. Foley-Wolthusen, unbelievably fundamental. Rotation can't break because it's just a change of basis. But if there's something in the problem that makes a change of basis not be helpful, then you've got to go back and sort of do the problem old-fashioned way. You have to do it with your teeth. Okay, takeaway message. Comments, thoughts?
By loosely, you mean that there's a direction variation? Like the losses are having an angular dependence?
It's nothing like that. It's much simpler. If you think about it, imagine that there's a space that is relevant to your Hamiltonian without the loss. And in order to do the rotation, you're taking this whole space and sort of looking at it sideways, tilting it, and you've got the whole space, and you've got the same problem. Now, if you have loss, if the loss is really, really strong, what that means is that part of your space gets eliminated largely by the loss. Namely, if the loss is strong, then the occupation probability for the space that are really lossy is really small. So you don't get a clean separation of the part of the Hilbert space. So now when you do your rotation, you're trying to take something that's got like an incomplete structure. Now you rotate it, and the part that wasn't complete sort of localized in one part of your Hilbert space initially. The rotation takes and spreads it all over the place. And it's going to take forever and a day to track everything down and implement it and make it work in the rotated frame. So it's more that kind of thing.
So you're just asking, why is this strip necessary? You don't have to perform that coordinate change.
It's actually much stronger than that. It's that if you do the coordinate change, if you do the rotation, the problem you get left over is an ugly mess that nobody's going to have any luck solving. But it's much easier just not to do the rotation, just grate your teeth and do the problem after. Okay, so the question is how to respond. We've now got some fine print, we now got a direction to go. So the question is now, what kind of physical model might we be talking about? So the simple Dirac proton model is really useful in terms of shedding light on the problem. But we want a theory for nuclei in general. And previously, I've described new models based on Dirac phenomenology for nucleons. Also described doing this based on quarks. And at some point, there's headaches with some of the models, but at some point, we probably shouldn't have to be solving nuclear problems in order to understand our condensed matter. There ought to be some approach that's like simpler. And what I want to talk about, so for example, previously, I wrote down Hamiltonian like this. So we got relativistic description for nucleons, relativistic description for electrons, and then electron-nucleon, well, basically Coulomb interactions between them. And so in principle, we've got to solve now for our nuclear wave functions on the same footing with our lattice. That's not good. Now the trick would be to do this. Start out with my nuclear Hamiltonian. Basically write it out as in terms of basis states. In terms of basis states, actually, of this rest frame version of the problem. And if you do that, then you can basically, then you work with the coefficients of the expansion of your rest frame expansion. But that's equivalent to a matrix problem that looks like this. And sadly, if you start from Dirac, the matrices that you get here don't satisfy all the nice relationships you'd like it to solve. Namely, you end up finding that the inertial mass is, the Newton mass is different from the rest mass and so forth for the Dirac problem because it's not covariant. So there's headaches, but this is interesting. It's a good first step. And if you do that, here's now a condensed matter Hamiltonian based on having a relativistic rest frame basis state description of nuclear states. So we have models coming out of this, and models that we can actually work with. And as I mentioned, there's a headache. Dirac problem is not, many body Dirac problems not Lorentz invariant. We'd actually like a better starting place. And a better starting place is to work with a relativistic field theory that is relativistically invariant. And if we do that, it turns out that we can do the same thing, and we get this kind of description, but now these matrices obey all the right kind of relationships. We actually now get a simple extraction of what we need out of the relativistic field theory. We get matrix equations. Now that when we say, well, these matrices, they're a mess. This has got positive energy states, negative energy states. It's ridiculously complicated. Yes, it is. Same goes for this. These things are messes. Namely, you would like never actually having to spell these things out. And within the model, as we apply it and use it, the parts of this which give rise to the non-relativistic kinetic energy basically stays intact and gives you the non-relativistic energy. The part gives you the coherent dynamics. Well, there's a few transitions that are going to behave differently. And you're allowed now to focus on the parameters associated with transitions in order to extract what you need to do to calculate things with it. So as it turns out, even though this sort of looks trivial, this is sort of ridiculously powerful because it allows you to pick and choose what you need out of a more fundamental model to describe your local dynamics. Now, suppose we do this. Suppose we make up a model based on this kind of approach now with a Lorentz invariant underpinnings. Now let's go back and do our Foldy-Waldhusen. We can do Foldy-Waldhusen and get this with clean separation. Everything relativistic, everybody's happy. And now, once we have it in this form, we can actually even choose our positive energy states and make sure that we're dealing with the positive part of the spectrum. So we recover everything that we do. In the negative energy states, they're part of the mathematical problem. They're not going to show up as physical states. So we get that separation out of the box beautifully here. Now, what about in the presence of loss? In the spin boson model, when we augment it with loss, we get efficient coherent energy exchange with multi-quantum transitions. If loss is present in this model, it basically does the same thing. And the way it does it is like interesting. So most of this ends up being what it was before, Foldy-Waldhusen would sort of make it work the way it did before. A few transitions here, like maybe the 1.5 kV transition in Mercury to 1, basically you could execute coherent dynamics on that, and the rest of the problem basically satisfies things that are essentially equivalent to Foldy-Waldhusen. When you go down and you roll up your sleeves and you try to and you solve the rest of the problem by hand, consistent with these things, you find that your answers are equivalent to having done a Foldy-Waldhusen for the rest of the problem. The part that you're extracting out is a very small part of the total interaction. Takeaway message. Well, you add loss, Foldy-Waldhusen becomes unhelpful. We now have a theory. And we've actually previously proposed this theory as a way to systematically describe Hamiltonian. In fact, I think last year I got up and I said, can solve now have a model now to describe anomalies. So we've had this model essentially for a year now. And actually, before going on, let me pause, takeaway message, questions or comments?
So this Hamiltonian, it is time dependent, is it? And in other words, the dynamics are a standard Hamiltonian evolution kind of equation?
It's a quantum problem, and the loss operator, I mean, I tend to use time-independent descriptions. I don't really like time-dependent descriptions for my Hamiltonians, but I tend to favor infinite order belong figure type description. But we can get Ehrenfest dynamics out of this in crystal straightforwardly. Also, the presence of a loss here means that this is a sector equation, and the loss term is a sector changing part. So there's something bigger that this is extracted from, which we have written in.
The mathematicians lately have invaded physics with the great enhancement of Hamiltonian mechanics using fancy Lie theory to extract conservation theorems. Is this leading to any conservation theorems that you have done?
That's beyond what I've been doing. What I've been doing is just nuts and bolts. I got a model. Now let's see if we can connect it with experiment, learn something, see whether it's right. What we're going to find out is that this is incomplete, sadly. Even after all my exhortations to the contrary, that this will do the job, still not enough, sadly. Let me try. Time's a little bit short, and when I was thinking of these few graphs, I recognized some would be a little bit short, so I'm going to be doing a little summarize. So I've had about a year experience with this model, and over the summer, I got a version of it up, which I thought was the cat's meow that would do the job. I got a version of the model that agreed with the Carboot experiment to as good as I knew the experimental parameters. It agreed with the excess heat experiments as good as I knew the experimental parameters. I was really excited. I was psyched. And in August, I presented this to my colleagues, wrote a conference, received papers, sent them out. And in October, I found an error in the models. So if you like, even though these models, this version of model that's out there and presented and so forth, they calculate out with experiment, in my view, better than any other model that exists. So they may actually still have some residual use. But the models are just simply in error, sadly. Let me talk a little bit about this. So I'm now going to talk a little bit about the connection between the model as an error and the Carboot experiment. And then I'm going to talk about the fix of the model. So in the Carboot experiment, the idea is that there's mercury in the gas, and the mercury gets sputtered into the surface. And this is a calculation of how far the mercury goes in. And so, for example, if the glow discharge were running at a kilovolt, and all that kilovolt was going into mercury ions, it would be going in, I don't know, 45, 50, just under 50 angstroms. So you've got a little bit of mercury going into the surface. Turns out, if you say that it goes in and we're able to substitute for the host, then you say, I have a random distribution of mercury atoms. Now, if they're all in phase, and I got a broad line shape, what energy is it going to come out in? Well, turns out you can go collimated, and you can say, at what energy would the random placement of mercury atoms, different positions, do the phases add up? And you get over the bandwidth, the energy bandwidth, you get one that's the biggest. And the idea is that for the superradiance that occurs to get your radiation out, this will grab all of the energy. So if you like, that's the connection between the line shape and the different energies that you get for the collimated emission. And so these calculations, it's over here, it's over here, it's over here, and so forth. So based on this picture, I said, well, how strong is the coupling for mercury, the mercury transition itself? By now we've done a few matrix elements. I said, well, you know, it's probably somewhere in the neighborhood of 10 to the minus 5. Maybe it's as small as 10 to the minus 6, maybe as big as 10 to the minus 4. So I said, well, let's take the model, we'll calculate against experiment. I know there's more than a microjoule. I think there's less than a millijoule of energy in the vibrational mode. And this basically tells me how many mercury atoms I have on the surface. And this, I assume, was my guesstimate for the experiment. It turns out this is the line for 10 to the minus 5th for the A value, the A matrix element from the model for that transition. And the guess as to where it should be is smack dab right in the middle of my independent guess, this is the experimental parameters associated with the carbon. So that model seems to be about as consistent as can be to within how well I know the numbers. Now, more important is that there are spikes associated with this X-ray emission. Now, in my previous existence, I used to do mode blocking and analyze pulses, and it's unbelievable how much information you can extract about a physical system that produces pulses. So I said, let's apply the model to pulse emission in the carbon strip. My model produces pulses, carbon sees pulses. So let's compare A to B and see what the story is. So the place where the story starts is that there's, in spin systems and magnetic fields, there's something called Rabi oscillations, where if you couple energy in on resonance, you drive the population from the lower state to the upper state. Lower state sort of goes sinusoidal back and forth. Well, in this system, if you have multi-quantum transition and it's on resonance, you drive the population back and forth. Instead of sinusoidal, it's this nonlinear. It goes down and then chunks on here, and it goes up, and then chunks on here, and goes down. So you get nonlinear Rabi oscillations out of the model. It's predicted. And if you're going to have superradiance, which is the only way the X-rays can come out in phase, basically there's an internal conversion, which is much faster than the radiated emission. And the internal conversion half-life is like 81 nanoseconds, whereas the radiated half-life is, I forget the number, it's milliseconds or something, a third of a millisecond or so. And so as a result, you need an acceleration of the radiative decay in order to actually get an X-ray beam. You need Dicke superradiance. Turns out Dicke superradiance is maximized during these Rabi flopping right in the middle. So as a result, in association with nonlinear Rabi oscillations, you would expect X-rays to be emitted in pulses. You have a model, so you can say, well, do the numbers agree between the model and experiment? So it turns out that the constraint equations from this model, now once again, the model I'm comparing against, I know is wrong. The foundation of it's broken, but it seems to do pretty well anyway. So the number I get from the energy stored, smack dab in the middle of what I'm expecting experimentally. The number of the Dicke number is smack on where I'd like to see. And this is an independent test, the last one, but this is giving me a value that's consistent with what I was expecting. And it turns out if you go like just a little bit up, a little bit down, you can't get any agreement at all with these stupid pulses. You get an angular divergence of the beam, and we get an area. And it turns out I have to assume an area smaller than the coin area in order to make the numbers work. And the beam divergence is within the experimental parameter regime. So the constraints on the parameters are much more severe for the pulses. And this broken model is ending up being consistent with this pulse emission, which is stunning. Namely, when I got the model, I said, okay, but I've killed 280 plus models. And what I do in life is I kill models. So having this model, when I did my first test, I was expecting it to break and die. And it didn't break and die, so I gave it this pulse test, fully expecting to, bury it in the backyard. And I got consistency here, which stunned me. I fell off my chair for this. So even though there's a problem with the model, it's already seeming that it's shedding light.
Can you give a one-sentence description of what that problem is?
I give a whole geograph description.
Oh,
of what the
okay.
problem is. So let me see. So I set up a model where the Mercury 2-1 transition, I don't have the strongly coupled transition, but it's doing all the work by itself. And in order to make it work, I assume that there's a very large number of very strongly coupled transitions, which is said sort of behaves as if you normally do Foley-Wolthusen. Well, in this model, I said, I don't know that, let me calculate what they do explicitly. So I made a calculation of what they did explicitly. And when I did it, I ended up introducing some additional fractionation power due to the coupling to these strongly coupled transitions. And that's what gave the good answers. And then in October, I went back and did it again, and dotting all the I's, crossing all the T's, I found that I screwed up. And then when I redid it and calculated right, I found that, in fact, there's no enhancement to the fractionation for the strongly coupled transitions. In fact, strongly coupled transitions and other ones all behave as if Foley-Wolthusen still worked. So something else has to help with the fractionation. And something else, so another dead model. Was something else. Actually, it was a good thing that this particular model was broken because the implications haven't been right, were unthinkable. So debugging, I needed something else to help with the fractionations. And I relied on the phonon nuclear coupling to do it. But it's too weak if you do it correctly. So the proposal now is to, in a metal, there's electrons present, the phonons coupled to the electrons. And the electrons can produce fractionation. And by now, I downloaded a couple hundred papers. I've been reading them, finally I've understood them. Usually electron phonon coupling in metals is done a block picture. But I kind of need to do more Oppenheimer in order to make sure I know what the phonon is and get my phonon exchange right. So it's taken forever and a day, but we now have a Born Oppenheimer formulation for this coupling to do the fluctuations. We've got this all worked out now. In fact, probably if I hadn't been teaching this course, I actually have a number from the stupid model now to see whether it works or not. But within, I don't know, weeks, maybe a month or something, I'll have numbers now from this electron phonon fluctuation model, and I'm going to know whether this thing works or not. Basically, it sort of has to work. I know qualitatively there's features of this model that are incredibly closely matched to the experiment. The older models basically said for excess heat, the harder you drive it, the more power you're going to get out. But in experiments, people find that the harder you drive it, there's an optimum, and then you don't get more power later on. This model works that way. This is the first model I have that works that way. Anyway, takeaway message. Takeaway message is that we have models now that are getting closer to experiment. We have models now where the physics starting place is getting better, better, better. This latest version will have some numbers out shortly. I'm of the opinion that this one's going to be it, that this is going to work. Conclusions. All kinds of conclusions. Conclusions. We're trying to model energy fractionation. We've identified Carboot experiment as an example of multi-quantum exchange between vibrations and nuclei. The model seems to be relevant for Carboot, and this connection has taught us something really important about the physics. And the physics has led to fine print on Foley-Wolthusen. And we're responding by putting together a new model that takes that into account. It was close to being done. Go back to my warning. For those of you who came late, this field's a dangerous field to be in, and it can ruin your career. And I'd like to close with a whole picture like that. When I was less weather-beaten and hadn't pulled out as much hair, that's what I looked like, and that's Martin Fleischmann. we were at the time discussing something having to do with cold fusion. One of my colleagues shot us. Okay, there's much more to talk about, but Mitchell's on Monday, and this is basically the end of my stuff. What I didn't get to was the nickel hydrogen system utilities and transportation hotspots and explanation for it. Explanation for the gamma sequence are nice to have done it, but I got wrapped up talking about this. So any final questions, thoughts, or comments before breaking? Okay, so the quiz is going to be
Oh my God.
okay. Well, thank you for your